There's a question that has quietly unsettled every physicist who has ever honestly sat with it. Not a new question, not a trendy one. In fact, it's so old and so fundamental that most professionals learn, at some point in their training, to stop asking it. They learn to calculate instead. They learn to predict. They learn to use the thing without understanding it. And that quiet agreement, that unspoken treaty between curiosity and practicality, might be the most revealing detail about the state of human knowledge that no one ever talks about. The question is about light, not about what light does. We know what it does. We can describe its behavior with extraordinary precision. We can bend it, split it, slow it, trap it, measure its wavelength down to fractions of a nanometer. We have entire industries built on manipulating it. Fiber optics, lasers, cameras, telescopes that capture photons emitted 13 billion years ago. We are, by every practical measure, masters of light. But what light actually is, that's where the mastery ends. That's where the language starts to break. And that's where most people, including most scientists, quietly change the subject. Let me explain why that silence is more important than it seems. Start with the simplest possible version of the question. You flip a light switch, a bulb turns on. The room is bright. What just happened? At the most basic level, you sent electricity through a filament. The filament got hot. It emitted electromagnetic radiation in the visible spectrum. That radiation traveled outward in all directions at roughly 300 million meters per second and struck the surfaces around you, bouncing into your eyes, where specialized cells converted it into electrical impulses your brain interpreted as brightness. That sounds clean, that sounds complete, but every single clause in that explanation contains a door, and behind every door is a room with no floor. Take the speed. Light travels at 300 million meters per second in a vacuum. That number is not arbitrary. It appears to be woven into the deepest architecture of reality. It is the speed limit of causation itself. Nothing that carries information can exceed it. But why that number? Why not faster? Why not slower? Why does the universe even have a speed limit? There is no derived answer. It's not a consequence of something deeper that we found. It simply is. The constant sits at the foundation of two of our greatest theoretical achievements, relativity and electromagnetism. And in both cases, it's not explained. It's assumed. It's the starting point, not the conclusion. And that should bother us more than it does. Now go deeper. Forget speed. Think about what's actually traveling. You were probably taught at some point that light is a wave. That's true. It diffracts. It interferes. It behaves exactly like a wave in dozens of well-documented experiments. Thomas Young showed this over 200 years ago with nothing more than a card with two slits in it and a candle. The pattern on the wall was unmistakable. Alternating bands of brightness and darkness, exactly what you'd see if two ripples in water overlapped. Light was a wave, case closed, except it wasn't. Because a century later, a quiet patent clerk in Switzerland noticed something that the wave model could not explain. When you shine light on a metal surface, it knocks electrons loose. That's called the photoelectric effect. And it's not exotic. It's how some solar panels work. But here's the problem. If light were purely a wave, then brighter light, meaning a wave with more energy, should always knock electrons free, regardless of color. Just turn up the intensity. More energy, more force, electrons fly off. That's not what happens. What actually happens is that the color of the light matters more than the brightness. Dim violet light can knock electrons loose. Blazing red light cannot. No matter how bright you make the red light, nothing happens. But even a faint violet beam starts ejecting electrons immediately. The wave model has no explanation for this, none, because in a wave, energy is spread out continuously. There's no mechanism for color to be the deciding factor. The explanation that emerged, and it came from that same patent clerk, a man named Albert, working on what he considered a more revolutionary idea than even relativity, was that light is not just a wave. It also comes in packets, discrete bundles of energy. Quanta, what we now call photons, and the energy of each photon is determined not by the brightness of the light, but by its frequency, its color. Violet photons carry more energy per packet than red ones. That's why they can knock electrons loose and red ones can't. It's not about total energy, it's about energy per unit. And just like that, light became two things at once, a wave and a particle, continuous and discrete, spread out and localized. This is usually where teachers smile and say the phrase wave-particle duality, as if naming the contradiction resolves it. It does not. Naming a paradox is not the same as solving it, and what's happened in the century since is that physicists have gotten extraordinarily good at using this duality without ever fully reconciling it. The math works. The predictions are astonishing. Quantum electrodynamics, the theory that describes how light and matter interact, is the most precisely tested theory in the history of science. Its predictions match experimental results to more than 10 decimal places. There is no theory in any field, anywhere, that is more accurate, and yet its creators were the first to say they didn't understand it. Richard Feynman, who helped build that theory, said something that should be carved into the wall of every physics department on Earth. He said, "I think I can safely say that nobody understands quantum mechanics." He wasn't being modest. He wasn't performing humility for a lecture hall. He was stating a clinical fact. The math tells us what will happen. It does not tell us why. It does not tell us what is happening between measurements. And when we try to fill in that gap with intuition or narrative or any picture we can hold in our minds, the picture falls apart. Consider the double-slit experiment again, but now with modern equipment. You can run it with individual photons, one at a time. A single photon leaves a source, travels toward a barrier with 2 slits, and lands on a detector screen behind it. If light were simply a particle, each photon would go through one slit or the other, and you'd see 2 bands on the screen, 2 clusters. That's not what you see. Over time, as thousands of individual photons land one by one, the pattern that emerges is the interference pattern, the wave pattern. Bands of light and dark, exactly as if each photon went through both slits simultaneously and interfered with itself. One photon interfering with itself. Now here's where it becomes genuinely disturbing. If you try to determine which slit the photon actually went through, if you place a detector at one of the slits to catch it in the act, the interference pattern vanishes. The photon behaves like a particle again. 2 clusters, no interference, as if the act of looking changed what happened. This is not a metaphor. This is not poetic language. This is what occurs in laboratories around the world every single day, and has been confirmed so many times that no serious physicist disputes it. The photon seems to behave as a wave when no one is checking, and as a particle when someone is. The observation itself appears to alter the outcome. You can feel the ground shifting under your feet when you sit with that long enough, and the natural response, the deeply human response, is to assume that we're missing something, that there's a hidden variable, some piece of information we haven't found yet that would explain the photon's behavior in ordinary terms. It's going through one slit, we just can't see which one. The randomness is just ignorance in disguise. That was Einstein's position for much of his life. He believed that quantum mechanics was incomplete, not wrong, but incomplete, that underneath the apparent randomness, there was a deterministic reality we simply hadn't accessed yet. It was a reasonable position, an elegant one, and it was tested. In the 1960s, a physicist named John Bell devised a theorem, a mathematical proof, that allowed this question to be settled experimentally. If hidden variables existed, certain measurements on pairs of entangled particles would obey a specific inequality. If quantum mechanics was right and there were no hidden variables, those measurements would violate the inequality. The experiments have been done, many times, with increasing rigor. The results are not ambiguous. The inequality is violated. There are no hidden variables. Not of the kind Einstein hoped for. The randomness is not a mask over deeper order. It appears to be fundamental, irreducible. The photon does not secretly know which slit it will go through before it gets there. It genuinely does not have a definite state until something forces it into one. And this brings us to what might be the most uncomfortable realization in all of physics. It's not that we don't yet understand light, it's that the universe may not operate in a way that is understandable in the terms our minds are built to use. We evolved to navigate a world of medium-sized objects moving at medium speeds. Our intuitions about how things work, that objects exist in definite places, that effects have causes, that observation is passive, those intuitions were shaped by survival, not by truth. And at the scale where light reveals its nature, those intuitions don't just become less useful, they become wrong. There's a particular kind of vertigo that comes with this. Not the dramatic kind, not the kind that makes headlines or fills lecture halls with gasps. It's quieter than that. It's the vertigo of realizing that the tools you've always used to make sense of the world, language, imagery, narrative, cause and effect, are not broken exactly, but bounded. They work beautifully within certain limits, and light is what happens when you reach those limits and keep walking. This is why physicists eventually stopped asking what light is and started asking only what light does. Not because they lack curiosity, but because the question itself may not have an answer in any language we currently possess. The math describes the behavior. The behavior is consistent. The predictions are confirmed. But the underlying reality, if that phrase even means anything, remains inaccessible to human narration. And yet most of us walk through our days bathed in the stuff. It's pouring through your windows right now. It's bouncing off this screen into your eyes at this very moment. You are swimming in something that the most powerful minds in human history have failed to fully comprehend, and you're using it to read these words. There's something worth sitting with in that. Not because it's frightening, not because it signals some failure of science. It doesn't. Science has done exactly what it's designed to do: observe, measure, predict, refine. The problem isn't with science. The problem is with the expectation that understanding should always feel like understanding, that the truth should always be something you can picture. That reality owes us a narrative. It doesn't. And light, ordinary, everyday, invisible until it hits something light, is perhaps the most elegant reminder of that fact. It is the thing we see by, and the thing we cannot see clearly. It is the medium through which we observe everything else, and the phenomenon that resists being observed on its own terms. There is a tendency, especially in how science is communicated, to present discoveries as puzzles that were solved, to frame history as a march from confusion to clarity. And in many cases, that's a fair description. We didn't understand disease, and then we discovered microorganisms. We didn't understand inheritance, and then we found DNA. The story moves from mystery to mechanism, and the audience feels satisfied. Light doesn't give you that satisfaction. Light gives you Thomas Young proving it's a wave, then Einstein proving it's a particle, then quantum mechanics proving it's both, then Bell's theorem proving it's neither in the way you thought. Each answer opens a deeper question. Each resolution dissolves into a more fundamental uncertainty. And at no point does someone walk in and say, "Here, this is what light is. Now you can picture it." Nobody has ever said that. And after a century of quantum mechanics, there is a growing, quiet consensus that nobody ever will. Not because we won't learn more. We will. Not because the physics is finished. It isn't. But because the expectation that we should be able to picture reality may itself be the error. The demand for a mental image, for a story, for something that behaves the way we expect objects to behave, that demand comes from us, not from nature. And nature, as it turns out, is not obligated to make sense to a species that has only been thinking for a few 100,000 years. This is the thought that tends to linger, not the experiments, not the math, not the historical anecdotes. Those are all fascinating, but they're not what stays with you at 2 a.m. when the room is dark and you notice the faint glow of a streetlight slipping through the curtain. What stays with you is the recognition that something that simple, light entering a room, is connected to a question so deep that it touches the boundaries of what human thought can reach. And the honest response to that is not frustration, it's not defeat, it's something closer to awe, but quieter. Something closer to respect, the kind of respect you feel not for a thing you've conquered, but for a thing you've met on its own terms and realized is larger than your capacity to hold it. That might be the most important thing light teaches us. Not what it is, not how it behaves, but what it reveals about the shape of our own understanding, its extraordinary reach and its irreducible limits. And if you've stayed with this to the end, then you've done something that most people, including most scientists, rarely take the time to do. You've sat with the question instead of rushing past it. You've let the discomfort be present without demanding it resolve into something neat. And that, more than any equation or experiment, is what real inquiry feels like. It doesn't end with answers. It ends with better questions. And the light is still there, filling the room, keeping its secrets, behaving exactly as it always has, indifferent to our confusion, beautiful in its precision, and utterly, fundamentally, irreducibly strange.